Yeah, hello again to statistics, and the last lectures we have generally talked about linear regression, but the simple linear regression where we have only these dependence between only two variables, y and x, and in this case, of course, we can also easily represent our data within a two-dimensional diagram. But of course, we then can also think about a more complex system that we would assume that in general we have one variable y again, which we want to explain. To be explained, but that we have many explanatory variables. Well, and in an economic way, of course, we started with this simple example where we counted visits and the impact on sales volume, but we can also think about what is our marketing budget, how many branches, how many stores do we have, how many people have we hired, and so on and so on. And well, that in general there is some function where we feed in, so to speak, our inputs, and here we obtain then our output. So also in general, we can say that you can think of here as the production function. So an example, production function in economics. Well, and this means maybe you have seen production function like input capital to the alpha labor input to 1 minus alpha. And yeah, in this case, we have a nonlinear dependence. And yeah, well, very often you will model dependencies between variables in a nonlinear case in economics. But what you find is quite often a function like this. And maybe you know this with a name. This is the so-called Cobb-Douglas function. And actually, you have seen this function also in this lecture already. Think of that alpha is 1/2. If we set 1 alpha, why do you have seen then this function also in this lecture? So if we set 1 alpha equals 1/2, then this would be square root of k times L. And what is this? What have we seen in this lecture? If we take the square root of the product of two numbers, what is this in a statistical interpretation? Maybe you have also talked about this in your microeconomics course, because how you should explain why you are using this function. So this is nothing else than the geometric mean of these two variables. Well, why do I give you this function in the case of multilinear regression? Well, we can manipulate this function here so that we obtain afterwards a linear dependence. Because what you can do, and very often we model in economics dependencies between variables with products and with these exponents up here, so as general geometric means. And how do we obtain from these general geometric means a linear dependence is if you take just logs of both sides, because then we have log y equals log of k to alpha L to 1 minus alpha. And what is this? The log of a product is what? What is the log of a product? The log of the product is the sum of the logs. This you have hopefully learned in class 10 or so in school. So, and if the log of the product is the sum of the logs, then we also know what is log of x1 squared, because this we can write as x1 times x1. So this is ln x1 plus ln x1, and this equals then ln 2 times ln x1. And this means if we have this exponent, this drops down just in front of the log. So this is then alpha ln of k plus 1 minus alpha ln of L. Well, and now we have here just a linear dependence between the logs. And this is very often done in economics in order to obtain a linear dependence, although the specific dependence is non-linear. Well, and this is then also the motivation that it is very interesting that we examine just this general multilinear dependence where we have many explanatory variables, and what we then want to do is to estimate our coefficients. Well, and now how does it then look when we have our data? So if we, for example, then look at the time series of a company where in years we look how many visits had we the first year, what was our marketing budget the last year, how many stores, how many branches did we have, and over time. So maybe you look backward for the last 6 years, and this then would mean that for every year I, for example, sorry, this has to be an I here. Oops. There. That your data point translates then compared to the simple linear regression just in this long row where we feed in our data. Well, and this writing we can then compactify within the vector or matrix writing. Because then we say, well, we have, for example, our first year. This is, for example, the visits in the first year. This is the volume of our marketing budget, and this is maybe the number of our branches. Well, and in order to obtain afterwards again this equation yi equals the sum of all parameters times the number of our explanatory variables, that we then write our parameters beta just in this vector. For example, remember what is the matrix 2, 1, 3, 4 times the vector 2, let's say 5. What do we have to calculate then? Because in some of the books I gave you, they use also this matrix writing notation. Hopefully you had vector and matrix notation within school or also in your introductory courses in economics. Do you remember how to multiply a matrix with a vector? Well, what you have to do is you take here the lines 2, 1 and then multiplying it with the columns 2 and 5. And what you have to do is taking the first number here times the first number in the vector and the second number here times the second number in the vector. So what you obtain then is again a vector with the first entry 2 plus times 2 plus 1 times 5, and the second entry would be then 3, 4 times 2, 5. So 3 times 2 plus 4 times 5. And if you calculate this, then it should be 926. And here you can also think of that you start with this line and then you multiply and sum up this with your parameter vector beta, And of course, in the end, when we compare this with our ansatz in the simple linear regression, where do I have it? I think it was just, oops, where do I have it? Oh, here I had the epsilon that in general in the simple linear regression we would have yi equals a plus bxi times epsilon I, and now we have this multiple writing, and if we feed in all our data, then we have also this vector of errors. So this is the vector of parameters. This is the vector of errors, and this is data, and this is data, and well, these vector of unity this vector of unity we need because we have also this starting parameter beta, which is not depending on one data of x. Well, and then if we just write this as a vector with this error, then with fat x, vector of beta, and vector of arrows, we end up with a similar writing of the simple linear regression. So compare with simple regression, and there we had y equals beta 0 plus beta 1 times x plus epsilon, and this we can then identify with a and b from the notation we have introduced by the simple linear regression. So it looks quite similar. And now what we are doing is, from the concept, that we are doing the same as we did in the simple linear regression. Because again, we just want to minimize the square of our errors, but now it is not just epsilon squared, but epsilon vector squared, and this is then nothing else than epsilon 1 squared plus epsilon 2 squared plus epsilon 3 squared, and so on. Again, just the sum of our errors. Well, and what is our error again? This is our data point, and this is the estimated regression. So this is then again y hat, the estimated regression. Well, and in vector notation, of course, then we have epsilon vector. This we find on the former slide. This can be solved for epsilon, and then we just obtain y vector minus x matrix beta vector. This we have to multiply twice, and for this hopefully you know also from school or from your introductory courses in mathematics that when you are multiplying vectors, that you then have to transpose the first part. So if we say, for example, the vector 1, 2 squared, this is then written that we have to transpose 1, 2 into a line, from a column into a line. So we obtain then 1, 2 times 1, 2, and then we can again multiply these two vectors in the same way as we did it with the matrix and the vector. So 2, 1, 2, 5, the line and the column. And here then also 1, 2 times 1, 2 means 1 times 1 plus 2 times 2. And this here, if we call this x vector, then this we write as xt, for t means transposed. And therefore you have here this t for the writing. Well, and then you have to know some rules how to multiply. Now, not just numbers, but vectors and matrices. The first one is then just yt times y, then the first component here, and this is then x beta in brackets t times y, then the other way around. So this one comes from here, and this one comes from here. And then, of course, these two, so-called a general square of this product of matrices and vectors. Well, and then hopefully in school you have also learned some rules how to deal when you are transposing one product. So if you multiply two matrices and transpose the whole system, then it can be shown that you have to interchange the matrices and transpose both matrices itself. That this is bt times at. And therefore, if you look at this part here, therefore we interchange when we want to solve this bracket here, that we just have to interchange beta then in the front and x to the second part, and the same we have to do here. So in this part also the places exchange between beta and x. Well, and what we can also do is that this part here can somehow so to speak, just be twice transposed. Because if you say t and transpose it again, then of course you end up with a itself. And if you do this with this term here twice, then you can show that this term and this term just coincide. And then you can sum up these two identical terms to the two. Well, and this, of course, you know also from the general second binomial formula. If you compare, then these result with a minus b squared equals a minus b times a minus b equals a squared minus 2ab plus b squared. And the only difference is that now we have here, so to speak, a general squared of our y, and here a general square of beta x. And this is then the mixed term 2ab in between. Well, and now we want to minimize this. This means we take this formula and now we want to vary all numbers of betas, and we want to fix beta at these numbers such that this term, the sum of the squared errors, will be minimized. Well, and this now means that we have to take the derivative of these products of vectors and matrices. But of course, the derivative, how to take the derivative, is done in the same way as you know it from just one-dimensional functions. Because we look then just in here and see we have at these places all our betas. And if we take the derivative, this will be then the so-called gradient of the function. So taking the derivative with respect to a vector is called gradient of the function. But yeah, you can think of that this is just your variable in a one-dimensional case. So I have here only one beta, and if you say, for example, f of x equals x times y, then f prime is just with respect to x, then this x becomes 1, and I obtain 1 times y equals y. So this beta in this term here just drops out. And here, this is then beta times beta, and this, you can more or less identify as in beta squared. But only you have here the general case that in between you have this matrix product, but when you take the derivative, you can take this as just in term beta squared. And if I have f of x, oops, not prime, equals x squared, then f prime is just 2x, and therefore if we treat this as beta squared, then if we take the derivative, we just write down the exponent in front of our function and lowering the exponent by 1. Well, and now again, the calculation rules are still the same in vector calculation and matrix calculation as you have this in the calculation just with numbers. Then we put this on the other side, dividing both sides by 2, and then we end up at this equation here. And well, we are interested in these betas, so we need then a condition for our beta. Well, and let's say if we have equation which is x equals y times beta, and then solve for beta. Then we would just divide both sides by y, and the division of y of both sides we can also write as y to the minus exponent minus 1 times x equals beta. And this we then do also in the matrix calculation, that we multiply both sides with the inverse matrix xtx. So times xtx with an exponent 1. This doesn't mean just writing here one line and writing down here xt times x, but then you have to calculate the inverse matrix. But remember again, all the numbers within x are known. And the y is also known, because this is all our known data. And if we then just have the inverse of xtx, this is nothing else than just this matrix transposed. All these data points are known. And then we have to multiply this with y, and then we just obtain our betas. So this is then the formula, general formula like what we had for b. I think it was xy bar minus xy single bar x squared bar minus x bar squared. So if we reduce this formula to the two-dimensional case only with one x and y, then this formula is nothing else than our a and b, which we had in the simple regression. Yeah, and also we can calculate the coefficient of determination in the same way. Again, it is just here the explained variance divided by the total variance. Remember, this is explained variance and this was total variance. And everything is just defined as we had it before in the simple regression, but only now in the multilinear case. Well, and yeah, this of course was everything quite theoretical, and now we will just go to an example. And in this example, we just say we have now data for our visits. This we take from our former example. We know the volume of our marketing budget, and we say within some region, within some branch, we want, or within some region, we look if we have there a branch or a store or not. And well, this is also in statistics quite often that you somehow have to quantify a qualitative statement. And then the question is, how do we model the situation that in one region we have a store, maybe in Jever we have a store, and in Shortens we have no store. And then we want to distinguish the impact. What is the impact on our sales volume if in one town I have a store and in another town I don't have a store? Well, I cannot feed in a regression somehow a verbal statement, but what I can do, I can just say, well, I then identify if I have a store in a town, then I say, in this case, I have a data with 1, and if I have no store in the city, then I model this with a 0. And this is then called a so-called dummy variable. And in this modeling, we can then identify the impact of the situation if I have a store in the region or the town or not. Yeah, and now please also open an Excel file, because now we want to start with our data. And now we can, so to speak, interpret this. A, B, C, D, E, F, G, H. This is our regions. And then in region A, we had 11 visits. We had a marketing budget of, I don't know, 33,000 euros. And here in this region, we have a store, and this implied then a sales volume of 30. And in region B, we had 8 visits. There we spent 30,000 euros for marketing, but there we didn't have a branch. But since maybe we make a good marketing, and therefore also in this city, maybe also via a web page or something else, we had a sales volume of 27. So all this is our data. And with this data, now I want to go into our software package. So let's copy this. And multiple regression. So, and now we have to identify our variables with X and Y. Well, sales volume, this is what we want to explain. So this is, oops, variable to be explained, and this are our explanatory variables. So in this case, we then can say that this is Y, and this is X1, this is X2, and this is X3. Now, what else do we need for our regression? And here we have just our optimality condition. So what we need is the vector of y. This we already have. But what we also need is the matrix X. And the matrix X does not only consist of our data for marketing budget, for visits, and for branches, but it has also this unity vector. And for this, we then take, when we want to have X, the input matrix would be then the unity vector and the data for our three explanatory variables. So this is then our matrix X. What else? We need X itself, and we need X transponed. Well, and X transponed, this we can easily obtain that we copy this data and if we paste it, you see this, yeah, make a right click, then you have a menu where you can choose here special options. Clicking on this, you have here this little square to transpone. Clicking on this, okay. Then, of course, just interchanges lines and columns. So this is then xt. So what we need further? Well, we need the product of xt times x. And this we can also do in Excel. And here the formula is just the implemented matrix multiplication. And this is called mult. And then you see here, what should I do? Array 1, array stands for matrix 1 and array 2. So array 1 is xt. So this one. And then with a semicolon, the next array or matrix. Closing brackets. And then you have your matrix multiplication. And now you have to be a little bit careful, because you see here, this is highlighted in a hole, so you cannot directly read out the data within here, because this is formatted as a matrix and not with for single cells. And this you can easily solve if you directly just read out the data here, and then it is not formatted as a matrix. So this was xtx, xt times x, and this is the non-formatted xtx, because what we now need is we need the inverse of this matrix. Well, and matrix inversion, this is not an easy thing. I think you have once used the so-called Gaussian algorithm for inverting it, maybe in class 9 or 10 in school. But well, this is an algorithm which in principle functions, but actually when you have very large matrices, it takes also a computer very, very long in order to calculate the inverse via the Gaussian algorithm. Then there is also the possibility to take the inverse via the so-called characteristical polynomial, or the so-called eigenvalues of a matrix. But if you calculate the eigenvalues of a matrix, you have the problem that if you have dimension which is larger than 4, then you get a polynomial of degree higher than 4. And maybe you have learned this also in school, that in general, a polynomial with degree higher than 5, higher than 4, so up from 5 and higher, that this is not in general solvable. So what was a polynomial? This was just f of x equals a plus bx plus cx squared plus cx to the power of 3 and so on. But what almost all software packages, what is possible for almost all software packages is that they can calculate the inverse approximately. And this you can do here also. And the formula is, I hope so, m in, no, this was not m inverse. Always, if you don't know something, then just ask the internet, because I forgot it. minf nur. This you can then just see it, and the formula is minf. So and you have to read in just the matrix, and then you get the inverse of this one. Well, again, this is formatted as a matrix, and therefore I just read out the data via copying it. What else do we have to do? Again, we have to multiply now our inverse matrix with the transposed X we already had. This is again only a matrix multiplication. So we go on, and this is then the inverse of this. Oh, formula war matrix multiplication, semicolon, and xt, and xt we had just here. So this is the same dimension as we have it here, and so this is this matrix times the transposed matrix, and the last one is we have to multiply now this matrix xt x to the minus 1 times xt with our input, our data input of the vector y. And where do we have y? Y is just these numbers for our sales volume. And this I'm doing then here. So equals this huge matrix. Again, the right syntax, mult times this matrix times now our input vector y. Oops. Oh, this is there. This one is wrong. Sorry. There. Oh, oops. Let's just, because I have forgotten to read out, this is also formatted as a matrix, so we have to read out this data. Equals this again. And now we can multiply this. So mult, the array here, semicolon, and read in the y vector, closing brackets, enter. Well, and this is now beta 0, beta 1, 2, and 3. Beta 1, beta 2, and beta 3. Oops. So in this case, we obtain then beta 0 is 7.4, 0.43, 7.42. Beta 1 equals 0.43. Beta 2 equals 0.46. And beta 3 equals minus 3. Equals minus 3.00. So we want also to calculate our coefficient of determination. For this, now we just feed in our data. So if we want to calculate here our estimated sales volume, then this would be nothing else than 7.42 plus beta 1 0.43, now the number of visits, plus 0.46 marketing volume minus 3.00, and if I have a branch or if I have no branch. Well, and what is the interesting result here is that these two numbers are positive. So from our data set, we can say that increasing visits and increasing marketing instruments will increase descriptively also our sales volume, but that we here in the last coefficient, if we have a store or not in our city, has a negative impact on our sales volume. But now we want also to calculate all this. So this would be then y hat, and this is then given by beta 0 fixing with the $2 plus 11 times 0.42 fixed plus 33 times beta 2 plus branch or not times beta 3. This we move down, and then we have to do all the same calculations as we did it for the simple linear regression. So what we need is y hat minus y bar squared, and we need y minus y bar squared. So y hat, at first I need to calculate y bar. This we obtain here. Arithmetic mean of our sales volume. And now y hat minus average sales volume, every number with respect to this number, and copying downward, and also for y, there we can use the same formula also with respect to y, but it is then not the column G, but it is the column F. Oops, here. So if we click in here, then you see sales volume, our data point, minus the average sales volume. Downward, copying. And then we need the sums, because the sum of this is again our explained variable, a variance. and this is the total variance. And then we obtain R squared as the explained variance over total variance. So to speak, our model explains somehow 72% of our variable to be explained sales volume. So R squared equals 0.72. Our model explains 72% of the total variance of Y. Well, let's also copy this. No, not this data here. Reformat it and downward here. And then we have the data also here. Yeah, of course, this took quite a long time, but I'm doing this with you because my hope is that then you understand a little bit more what is regression, what are all these formulas about, and you are not just in quotation marks a stupid applier not knowing what to do, because of course we have also within Excel a formula or an implementation that you directly can calculate the multiple regression, and this is then called RGP. And what you see here, yeah, you see it. First, I need all our Y values. This is this one. And then I need our X values. These are these one. In this case, of course, you don't need the unity vector. And I don't know, does this directly work? Yeah. So, and you see here just that it is another format which you have, because here this is then beta 1, beta 0, and this is beta 1, this is beta 2, and this is beta 3. And then you are done. But in my opinion, just giving you this formula here and explaining it only theoretically, then I don't know if students really understand what they are doing. Save this and going back here. Well, but now we have to admit that still we are only doing descriptive statistics. Oh, here I have also this. Then let's feed in also all this data here. That we have it also within our y hat, y minus y bar. I think then this has to be copied within here and the two sums here in order to calculate r squared. And we can also put in, I think first again to read out this data and put it here, this one here, this one here, and this one for beta 3. And let's do also r squared in order to keep complete as 72%. And we also can write down this is 220 for 3 over 308. Yeah, in order to end for today, still we cannot say how much we can rely on our model. And this just means still we have only a correlation, but we have no causality. So what we are doing until this point in the lecture, we doing only descriptive statistics, and we cannot deduce from descriptive statistics causality. And this is maybe the most often done error which people are doing, just asking many people, do you like the product or not? And then you are interpreting this as causality, that everybody likes this product if maybe 87 out of 100 people say that they like the product. So please don't mix correlations and causality. And the reason for this is just, well, we are not asking, for example, all people in Wilhelmshaven if they like this product. And from purely descriptive statistics, we cannot make then the conclusion that in general everybody likes the product. We do not know the whole population because in general we have just only survey data. But of course, in general, we want to make conclusions. And this we will then do in the next lectures, that we can show under specific assumptions. And well, maybe the most important assumption is about the error terms. When we assume that these error terms follow some special distribution, or what I've already talked a lot about in general, then that quite often it can be very good motivated that we just assume that these error terms are normally distributed, then we can, with a specific probability deduced from our data, from our survey, that, well, I can say then maybe with an error probability of 5%, we can conclude from our survey that everybody likes the product in Wilhelmshaven. And how this is done, this we will see in the next lectures. Okay, then very much, thank you very much for today.